Hi dear students, today we shall come a new video of class 9, that is propagation of sound waves. Propagation of sound waves. Okay, I think in previous classes you have learned little about sound as well as wave also. So here the same concept will repeat and we'll add little more concepts. Okay, so let's start a question answer round, and I think that will be easier for you to understand what is it and what do you understand by that. Number one, what is sound? So you can say that it's a very easy thing that you have asked. So it is a form of energy which creates a sensation of hearing in our ears. Okay, that is a very common thing. We all know that. Number two, how does it propagate? That is also a very simple thing. So we all know to propagate sound from one point to another point, we need a medium. If there is no medium, then sound cannot able to propagate through it. Why it needs a medium, that we have to discuss little later. But we all know we need a medium. Number three, how does it propagate? So next one, when the sound propagates, what does happen with medium? So what will happen when sound propagates through the medium? We all know when sound propagates through the medium, the mechanical energy of the medium changes. What is mechanical energy and how it changes? Okay, mechanical energy means the energy which is possessed by the particles due to the position of rest as well as due to the position of motion. Simple thing, the potential energy and kinetic energy of medium. Simple thing, when sound propagates through the medium, so the particles which are staying in that medium, their movements are changed. So it is clear for that reason the potential energy as well as the kinetic energy of that medium change. So together we can say mechanical energy of the medium change. So due to the propagation of sound, as the mechanical energy is changed, that's why it is known as mechanical wave. Okay, so sound wave is known as mechanical wave, or in another way you can say that as sound needs a medium to propagate, so that's why it is known as a mechanical wave. The reason behind this name, the mechanical wave, is that due to the propagation of sound through our medium, the mechanical energy of the medium changes, so that's why it is known as mechanical wave. Now question number 4. Okay, so in question number 4, the next question we'll ask, that is what should be the properties of the medium to propagate sound. So as we have already told that we need a medium to propagate sound through it, so there must be some special characteristics or requisition of that medium so that it can able to propagate sound through it. Okay, so what are the properties? Number one, the particles in the medium should be elastic. The particles in the medium should be elastic. What does it mean? It means that first I will discuss a little bit about elasticity. So whenever anyone just asks about elasticity, the simple thing that comes to our mind, a rubber band. If we stretch the rubber band, the length of the rubber band is increased. If we just omit the force, then it just get its previous shape. Okay, so simple thing, by the application of force, when the shape is changed of a substance, and due to the abolition of the force, it will just get back its own shape. That property of the material is known as elasticity. So the particles in the medium should be elastic. That means when the sound propagates, the particles in the medium should displace from its place, and when it propagates through the particle, after that the particle will reach at its own position. That is known as the elasticity of the medium. When the sound propagates, the position of the particles get changed, and when it propagates a long distance, that again that particles come to its own position. That is known as elasticity of the medium. So to propagation of sound through a medium, the mediums should be elastic. Number two, that is also very interesting, the medium should have inertia. What is inertia? We have already learned. Inertia means it is a property of the particle to stay at its own state, either in a state of rest or in a state of motion. So the medium should have inertia. So medium means the particles in the medium should have inertia. What does it mean? Mean inertia is a property which is directly related with the mass. So the particles should have definite mass, and as they should have a definite mass, they should have a particular mechanical energy. Because we know in kinetic energy or potential energy, whatever we have gone, it is directly related with mass. So if there is masses in the particle, then they should have a proper mechanical energy. So whatever the medium we will choose, they should have a perfect inertia. That means a perfect combination of potential energy and kinetic energy. In total, the mechanical energy. Number three, and this is the last property. The medium should be frictionless. The medium should be frictionless. That means when the sound propagates through a medium, what is friction? We have learned in the previous chapter only that friction is the force which acts opposite to the motion of a body in a contact, when the body contact with a plane. So simply when the sound propagates through a medium, if the medium should have friction, then there is a opposition force which just try to prevent the sound propagation. Okay, so some of the sound energy will be lost to get rid of this frictional force. Okay, then what sound you have propagates, that sound will not reach to the another person, because some of the sound energy will be lost due to the friction. So what medium we have to choose for the propagation of sound, that medium should be frictionless, so that what sound we desire to propagate, that perfect sound should be gone to the another person. Okay, so here we have discussed about four questions, and we have got the answers of all the question. Now we have to come with the question number 5. So we have come to discuss about question number 5, which is a very fundamental question, that how does the sound produce? In the previous questions, we have learned that how it propagates, from where it propagates, everything we have discussed. But how does the sound produce? Simple thing, if I have told you an example, assume you are having a string and you have just tied it up in two terminals, and if you plug at one point, okay, then it will just vibrates by this path, the string, up and down, and we will just can able to listen, we can able to listen a sound from here. Okay, so if I hit a bell, so assume in the temple this type of bells are there, no? So if I hit it, it will just strike on this point and then it starts vibe, then the sound comes. If we just touch here, we'll feel there is a vibration going on in the whole bell. So from these two experiment, we can say that the main cause of producing sound is vibration. Okay, so vibration of a body. So when a body vibrates, then only the sound produce. Now the question has come, any vibration can produce sound. So here also I am vibrating the pen here. So no sound is produced. So not all the vibration produced sound, but for producing sound, vibration is needed. That is the important thing. Coming to question number 6, that is also very important. Why does a medium is needed to propagate sound? See, in the previous questions we have discussed that we need a medium to propagate sound. When the sound moves through a medium, then the mechanical energies are changed, all that things. But why the mechanical energy should be changed? Why does the medium is needed to propagate a sound? So for that thing, I'll show you one experiment here. So to do that experiment, I will take one tuning fork. What is a tuning fork? A tuning fork is a Y-shaped rod. If you hit it by a hammer made by rubber, then this rod will start vibrating and then one sound is produced from it. Okay, so assume one rod I have taken, this tuning fork I have taken, and this is the medium. The medium I have represented by some equidistant parallel lines. Now you might be asking, sir, what is the reason behind it? Why you have shown it by some equidistant parallel lines? The reason is that when there is no sound in the medium, that time we assume that the density of the particles in the medium are same, are in equilibrium. Means at every point the density is same. Clear? Whenever we have hit it with a rod made by rubber to it, then this tuning fork starts vibrating. So how does the vibration produce? What is a vibration? So if I define vibration, we all know that when a body moves to and fro from its mean position. So assume in this body there are two rods, one we are taking A, one there is B. We are following the B rod. The A rod we will not follow because the A rod is in left hand side and here we are not assuming any medium. Okay, definitely in practical there should be medium, but we are mainly focusing on the rod B. So from the mean position, that means it is its mean position, it will move to and fro. That means one, it will move to right hand side, means from B it will come to point B dash, and then it will come here. So when it will go B dash, okay, in the part of a vibration, then what will happen? As it moves right hand side, then the particles of the mediums get attracted by it. Initially no vibration, no attraction, but when the vibration starts, as the position of B is changed, then the particles of the mediums are attracted towards it. So when they are attracted, then the distance is closer, but the particles which are very much nearer to that tuning fork, they are only attracted. Then rest of the particles, they are at a long distance. Okay, so initially the distance are equal, but when you start vibrating the tuning fork, then the density nearer to that portion, it is increased. The density of the medium is increased there, and here in this case the density is decreased. So this portion where density is increased, that portion is known as compression, and here the density where the density of the medium is decreased, that is called rarefaction. So that one you have to learn earlier also. Again I have explained you so that you can clearly understand and correlate our concepts. Next one. So as from B dash position it has reached earlier, so initially it goes from B to B dash, then from B dash it will reach to the point B. Simple thing, it moves towards the B dash and then it will come to the point B again. When it will come to B, then the particles of the medium, again very much long distance, they will go far. But as they will go far, these particles at a far distance, they have come closer together. Okay, and seems to be like that this compression is come here, and here a little bit rarefaction zone is created. And now from this portion, this tuning form, here it is B, and now it is coming in left hand side. Assume it is B double dash. Okay, we are just talking about B. So here from the mean position it is coming towards left. So as it comes towards left, that means it is moving away from the medium. So here the rarefaction zones are created, and at a long distance compression is created. So in this zone, rarefaction, and here there is compression. So if we see it together, it seems to be like that when a vibration is occurred, this compression is moving from here to here to here. So the compression is moving. So as the compression is moving, the consecutive rarefactions are created, and by this way the sound propagates through a medium. Assume if there is no medium, so no medium means no particles, and no particles mean no compression rarefaction. So as there is no compression rarefaction, so there will be no sound. So if it is asked to us how does the sound propagates through a medium, then the answer will be by making consecutive compression and rarefaction. Okay, so the density is changed. So as the density is changed, so here you can correlate the previous concept, the mechanical energy that will change when they will come closer together. Definitely the particles who come closer, then the kinetic energy will be increased. Okay, and as the distances are changed, then the potential energy will be changed. So by changing the potential and kinetic energy, the sound propagates through a medium. So here, when the sound propagates through a medium, one thing we have seen, the compression and rarefaction is created. That means the density of the medium is changed. That means a disturbance in the medium is created, right? Initially, no sound, no disturbance. As the sound propagates, so there is a disturbance created in that medium. And we know when there is a disturbance created in a medium, that is known as a wave. So we can conclude from this experiment that sound is a wave. As the sound propagates through a medium, then it creates disturbance in it. Okay, so that means sound is a wave. Now one new term comes to you, that is wave. Though it is not new term for you, you have already learned wave in the previous classes, but in this class also we will learn little bit about wave. So our next target is to learn about wave. Wave, what is it? Now just now we have told wave means disturbance in a medium, that is known as a wave. Okay, the disturbance created in a medium, that is known as a wave. So how many types of waves are there? So wave is of two types. Number one, transverse wave, and number two, longitudinal wave. So here I am going a little faster because you all know about the wave and what is it. What is transverse wave? Okay, so it is clear, if the vibration of the particles are perpendicular to the propagation of the wave in a medium, that is known as a transverse wave. Vibration of particle are perpendicular to the propagation of wave. Simple thing, if the wave propagates in this direction, then the vibration occurs perpendicular to it. So in this direction, these are the perpendicular direction. In this direction, the vibration will occur. That type of wave is known as a transverse wave. Let's see an example. Simple thing, if you have thrown a stone on a pond, then what we will see? We'll see if the stone is just fallen at a point here, there will be a continuous ripples are created at the pond, like this way. And if I want to show it linearly, the water level will increase, it is decreased, then it is increased, it is decreased, like this way. Okay, so if you put a very light object there, so you will see the object will come at the top, then it will reach here, then again it will come at top, then again it will reach at down. So like this way this movement is going on. That type of vibration is known as transverse wave. Why? Because as you have thrown the stone here, we have seen the wave is propagate radially outward, means as the ripples are created in circular path, so the waves are propagating towards the radius, and the vibration we have seen that in this point the level of the water is increased and here the level of the water is decreased. So the vibration of the water is just like upward and downward, that means perpendicular to the propagation of wave. Wave is propagating radially outward and the vibration is occurred perpendicular to the wave. Okay, so this type of wave is a transverse wave. Okay. Now, in this case, we have to mention two things. One, when this perpendicular vibration occurs in positive direction, means in upward direction, so the maximum vibration in upward direction, it is known as crest. Okay, and the minimum means downward vibration, that is known as trough. Okay, so here it is crest, here it is trough. So if anyone asks you how does the transverse wave propagates, the transverse wave propagates by creating continuous crest and trough. Crest means the maximum vibration in upward direction to the propagation of wave, that is known as crest, and downward maximum vibration is known as trough. So by making continuous crest and trough, the wave, transverse wave propagates. Now coming to the longitudinal wave. What is longitudinal wave? And here told that vibration of particles are parallel to the propagation of wave. That means in which direction wave propagate, the vibration is also occurred in same direction. Means in that direction only the vibration occurred. Sometime it is stretched, sometime it is decreased. Simple thing. If we are having a spring, okay, and here a mass is given, and when you have applying force here, we know the spring will squeeze and then it will expand. So that is the vibration we have seen for the case of longitudinal wave. Okay, and whatever we have seen for the sound wave also, by creating continuous compression and rarefaction, that is also a longitudinal wave. So simple thing, we can conclude here that sound wave is a longitudinal wave. Fine, because in which direction sound propagates, the particles in the medium vibrates along parallelly to it or along the same direction. So that's why sound is known as a longitudinal wave. So that is a short story of wave. Okay, so now we have to see the representation of wave. So how does we have to represent a wave? So generally we have represented it in a form of graph. So first graph we have to show, that is known as displacement time graph. So already we have told that wave is nothing but a disturbance in a medium. So if the disturbance occurs in periodic order, then we have to see the displacement of the particles. It's just like occurred this way. Now you might be telling the sir, so that is a displacement you have shown here of the particles for transverse wave only. So what will happen for the case of longitudinal wave? So when it is occurred for longitudinal wave, so here you see, in this case for longitudinal wave, whenever we have to draw the displacement time graph, so the compression and rarefaction is occurred. Compression means the particles are come closer together, and that displacement we have taken positive. So as that displacement we have taken positive, so that will be written as this. And for rarefaction, that displacement we have taken as negative. So if I have told the representation of displacement time graph for both transverse wave and longitudinal wave, both are same. Don't be confused that it is seems to be like transverse wave and longitudinal wave we cannot able to represent like that. It is a wrong concept. Okay, here also displacement is occurred in positive direction, so that's why we are taking this one is crest and this is trough. And for the case of longitudinal wave, the displacement occur due to compression. That one we have to take in positive. So that's why it is compression and it is rarefaction. So very simple thing. So that is a displacement time graph for a wave. One more graph we have drawn. That is known as displacement distance. So distance means how much distance is covered by the wave. How much distance is covered by the wave. So that also represented by this, because we know the wave always propagates. The wave cannot able to stop in one place. So if it is, you can say it is transverse and this is longitudinal. So the representation will be same for both the wave. Okay, so here distance and displacement. So both representation of transverse and longitudinal both are same. So don't be confused here. You might be confused that sir, in the case of whenever we are talking about longitudinal wave, so the wave is propagating along this side, so we are taking distance. So why we are taking displacement is perpendicular to it? Because we have seen the displacement is parallel to it. But here the compression we have shown that here the particles come closer together, so that's why that displacement. So when the particle come closer together, there also a displacement is occurred. That displacement we have taken a positive displacement, and when they move far, that should be taken as negative. So that's why we can represent it like this way. That is a representation, that is not a wave, that is a wave representation. Now we have to discuss about some terms related with the wave. So once we have drawn the graph, then it will be easier for us to discuss about the terms related with the wave. So whenever we are talking about the terms related with the wave, the first term comes to our mind, that is very easy, that is amplitude. What is amplitude? You all know. The maximum displacement occurs in either side of the axis or of the propagation of wave, that is known as amplitude. The maximum displacement. Okay, so this length, that length is known as amplitude. So amplitude is generally denoted by meter or centimeter. As we are just denoting displacement, so it is denoted by meter or centimeter. Clear? Okay, for the propagation of sound, as we have discussed about sound, so that's why all the thing we will discuss on the basis of sound. Okay, now whenever we are talking about amplitude, next term will come the time period. What is time period? Now to complete one wave, how much time it will take, that is known as time period. Complete one wave means the wave starts from here, it will coming to zero again and it will reach here. So from this point you will see again the same thing. From here again the same thing. So we can say this is a complete wave. Clear? So to complete one wave, how much time is taken, that is known as its time period, and which is denoted as second. Okay, whose unit is second and which is denoted by capital T. Amplitude is denoted by capital A. Okay, not going too much details, you all know that. Frequency, the number of vibrations or the number of waves per unit time or per unit second is known as frequency. The number of waves per unit time or per unit second. So if we see the time period is t, so in t second, how many waves are created? In t second, one wave is created. So in 1 second, how many waves? 1 by t. Okay, and this 1 by t is known as frequency. So what is frequency? Frequency is nothing but number of wave or number of vibrations per unit time. So what should be its unit? So its unit should be 1 by second and it is known as hertz. Okay, it's denoted by Hz. That is our frequency. Now we have to come to another thing, that is wavelength. What is wavelength? Okay, so for wavelength, the graph should be changed. Initially, we are discussing about displacement time graph. So that's why we have shown time along x-axis. But whenever we are talking about wavelength, then we have to take a displacement distance graph. Okay, so what is wavelength? Now to complete one wave, how much distance is covered, that is known as wavelength. Okay, so that means to complete one wave, how much distance it covers? This much. Okay, so that is known as wavelength, which is denoted by lambda and whose units is meter or centimeter. A very simple thing. So if I am talking about for a transverse wave, this is a crest and this is also crest. So the distance between two crests are the wavelength. In another way, we can say the distance between two trough for transverse wave, that is also wavelength. And for the longitudinal wave, we can say that the distance between two consecutive compressions are known as is known as wavelength, or the distance between two consecutive rarefactions, this is also known as wavelength. Okay, so wavelength can be represented by various manner. If it is told to you the distance between two consecutive compression is this, that means how much, what is the thing is given to you, the wavelength is given to you. If it is told the distance between consecutive compression and rarefaction, assume it is 5 meter, it is told to you. That means what is given? Compression and rarefaction. This length is given. So this is rarefaction. So if I draw a straight line here and this is compression. So this distance, it is half of the wavelength. That means lambda 2. Okay, so that should be half of the wavelength equals to 5 and wavelength equals to 10. So this type of things you should remember. Clear? Last quantity, that is wave velocity. So it is very clear, the distance covered by wave per unit time, that is known as wave velocity. The distance covered by a wave per unit time, that is known as velocity. So we can say that in t time period, the wave covers a distance equals to lambda, because t is the time period and time period means to complete one wave, and when one wave is completed, how much distance is covered? lambda. So we can say in t time period wave covers a distance lambda. So velocity v equals to, we can say that distance or displacement by time, that is lambda by t. Okay, by that way we can able to find it. Again 1 by t equals to f, that is frequency. Just now we have seen that 1 by f equals to frequency. So if I put here, so v equals to f into lambda. So that is the relation of wave velocity. That is, we can able to find the velocity of wave by measuring the frequency and wavelength. By taking the product of these two, we can able to find the wave velocity. So assume it is given the frequency of a wave, it is sound wave, we can say that it is 500 hertz. Okay, and lambda, it is given to you, assume 2 meter. So the velocity v will be 500 into 2, that is 1000 meter per second. If the wavelength given is another unit system, assume the frequency is given, if the frequency is given 10,000, not 10,000, we can say that the frequency is given 10 to the power 5 hertz. Okay, 10 to the power 5 hertz the frequency is given, and wavelength lambda is given to you, that is uh, 5000 angstrom. Then what will be our velocity? So we know 5000 angstrom means 5000 into 10 to the power 10 meter. 1 angstrom equals to 10 to the power 10 meter. So it will be 5 into 10 to the power 7 meter. So put the value here. V equals to F, that is 10 to the power 5 into 5 into 10 to the power 7. Okay, so it will be multiplied, I'm sorry, 10 to the power minus 10, I'm very sorry. 1 angstrom equals to 10 to the power minus 10, so it is 10 to the power minus 7. I'm extremely sorry. So it is 10 to the power minus 7. So it will be 5 into 10 to the power minus 2. So the velocity will be 0.05 meter per second. Okay, so this way the velocity we can able to calculate if the frequency and the wavelength is given to us. Similarly, if the velocity and frequency is given to us, we can able to find the wavelength, or velocity and wavelength is given to us, we can able to find frequency. Okay, thank you.